We'll start recording. In my last class, I think it was Duncan. Duncan decided he did not want to do a whole lesson today. And so I don't know why, but he was like, hey, can you take your whole lesson, which is about 3 pages of notes, and make it be 3 points? And so I did. And it was kind of fun. So you want a super condensed version of this lesson? We can make it wrap it out in about 3 points. I think let's do that. This is absolute value functions, and you've already seen all of this before. So we're kind of going over and maybe looking a little bit deeper at a couple of things, but not really. Okay, so I really liked how it went, where we just kind of took all of this information and we went like this with it. Is that okay with y'all? Okay, so this is going to be lesson 3.6, and the title is Absolute Value Functions. Absolute value functions. And what you know about these is that they make the V. Right? This is your toolkit function. They make a V. V for value. Yeah. One fun fact about absolute value functions is they can often be graphed as a piecewise function. I don't know if you guys remember doing the piecewise function, but let's say f of x equals the absolute value of x. That's equal to the function in pieces, 2 different branches. And on the left side, or on the right side of that equation, we'll call that the place where x is greater than 0. That's this positive area over here. X is greater than 0. That's this side. If you were to only look at this portion of the graph, what would the equation be? Think about it. What do? We start at 0. At 1, what's the output? Absolute value of 1. 1. Absolute value of 2. 2. What does this guy look like? Only on this side of the graph. 1, 2, 3. The identity function, right? It looks like the graph y equals x. That's true. If I'm only looking at this piece where x is greater than 0, we're graphing the line y equals x. This is the place where x is greater than 0. What do we graph it on the left side? If x is less than 0. So over here. What's the function? Negative x. Good. If I input negative 1, I output 1. So these are all the same numbers, but backwards. Negative. Opposite. If I input negative 2, I output positive 2. Do you notice that this is your identity function? Except slope is negative instead of positive. Still starts at 0. Right? So really, any absolute value function, wherever you move it, could be looked at as one branch on the right side of your number and one branch on the left side of your number. That's a kind of a fun fact about absolute values. They could be broken down and graphed in pieces, like piecewise functions. And in fact, in years past, this is how I've taught these. I made it where we had to graph each line, and you found out where they connected based on the domain of x. Kind of interesting. Okay? Y'all don't have to do that. That's not how this textbook does. But if you did, you could. All right, so that's fun fact number 1. There's 1 point for today's lesson. Remember, I'm only doing 3. The second thing I want to look at is a problem that we had on the test. There was an absolute value test question, and on many of your tests, I wrote, reflect, then move. Reflect before you translate, okay? So I want to walk through the order again. That order matters big time. So we're going to graph. This is going to be point number 2 here. We are graphing f of x equals negative 2 times the absolute value of x plus 3 minus 2. And I want to list out the things that we know have happened to this toolkit function. What's the first thing you know happened? Dilated, stretched by, stretched by a factor of 2. This is called a vertical stretch. We haven't necessarily talked about horizontal stretches. I'm kind of saving that for pre-cal. No, it's a thing. It's out there. We'll touch on it today, just very briefly. But this is a vertical stretch by a factor of 2. What else? Reflected. This is the one that got out of order on our test. What else happened? Left 3. How do you know it went left? Insiders lie. We're looking right here as our horizontal translation. And if that's x plus 3, this guy's going left 3. Insiders lie. And then down 2. Outsiders tell the truth. So this negative 2 means it goes down 2. Cool? So I would always start by graphing your toolkit function, which is going to be 0, 0, 1, 1, negative 1, 1, 2, 2, negative 2, 2. Right? Get that guy on the graph. Wowzers. I missed all the dots. It is so hard to graph lines on this thing. And then stretch it. Stretch it first. So we're going to take each output value and multiply it by a factor of 2. So instead of being at 1, 1, it's going to be at 1, 2. And negative 1, 2. And instead of 2, 4, or 2, 2, it's going to be at 2, 4. And I'm just going to kind of sketch through those dots. I know that's not my final result, but I do want to see it. Then we reflect. Okay, this is where a lot of us went wrong. We moved it before we tried to reflect. Flip it here. Okay, so for every output, I'm going to have that exact same output, but mirrored below the x-axis. So we're actually dealing with this line. Is that cool? Now we can move it. We're going to take each dot and drag it left 3. So 1, 2, 3. And down 2. 1, 2. This is now my new corner spot. This is going to be at negative 3, 2. Left 3. Down 2. I'm going to outgrow my graph here pretty quickly. Any questions on that? Can I show you a spoiler? Something that's going to maybe break your heart, but maybe make you really glad I'm telling you about it. You can find your new vertex by taking this value, this is C, and this value, this is K. Okay, K for vertical. A lot of times instead of C, we've used the letter H here, X minus H, right? Your new vertex is going to be located at negative H, K. Negative H, K. Vertex meaning this corner spot. The turning point of the absolute value function. H is negative in my ordered pair because insiders lie. So if that's a 3, my new vertex is going to be found at negative 3, negative 2. K tells the truth. Can you see it? Okay. And then this number A, this is the slope of the branches. That's the slope of the branches. So if I count down here, I went from the vertex down to run 1. Down to run 1. Count on yours and see if that holds true. Down to run 1. I know to go down in 1 because it's negative. Can you see it? So your stretch factor turns out to be the slope of these two lines that you're drawing. Is that helpful? A little bit? Okay, so there's some practice there. You are going to have some more graphing of these on your homework. And then here's my last point. Last piece of information for you today. One of your homeworks is going to say, find the intercepts. Find the intercepts of the function. Well, we've got two kinds of intercepts. Okay? And let's think about absolute value functions. Will absolute value functions always cross the y-axis? I'm going to draw several here. Do they always guaranteed to cross the y-axis? Yes. Answer is yes. Why is that? What's the domain of the absolute value function? Negative infinity to positive infinity. Perfect. Which includes x equals 0. It will always cross the y-axis. It's infinite. It's continuous. So no matter where it begins or where its vertex lies, one of the branches will always extend all the way forever and ever through the x or through the y-axis. Does it have to always touch the x-axis? No, this one doesn't. This guy's reflected and scooted down. He doesn't touch the x-axis. Okay? So in order to find out where those intercepts are, where it crosses the x-axis, where it crosses the y-axis, we're going to take just a couple of notes, and then you'll know how to do that. What's another name for x-intercepts? Zeros. X-intercepts, also known as zeros. I love it. Also known as solutions. One more. Starts with an R. Roots. Roots. So to find x-intercepts or zeros or solutions or roots, we set f of x equal to 0 and solve for x. Set f of x equal to 0 and solve for x. This is how we do this. Okay. How do we find a y-intercept? Okay, so think about it. If I want to be on the x-axis, I set y equal to 0, and that puts me on the x-axis in a place where y is 0. I'm not up or down at all. F of x equals 0 here. How do I find a place on the y-axis? Plug in 0 for x. This puts me on the y-axis here. Plug in 0 for x. That means 0, x is my 0. Is that making sense? So we're going to plug in 0 for x and evaluate. So one word says solve for x. I'm going to be working backwards there. One word says evaluate. That means I'm going to plug it in and see what happens. Okay. This is going to take us straight into your homework. And I have number 9. You have to work 10, 12, and 14 on your own. So I thought I would work number 9 with you. Cool? This doesn't count as one of my 3. This is still number 3 of my points. Okay. Y'all need to liven up a little bit. What's wrong with you? Y'all are okay? So our instructions here say find the intercepts. Find the intercepts. So this is number 9. And f of x is equal to 4 times the absolute value of x minus 3 plus 4. And I think let's do x-intercepts first. What was the rule on x-intercepts? Go back and look at your notes. Set it equal to 0. So we're going to take our function f of x and we're going to set it equal to 0 and solve for x. And you've done this before. You have set absolute value functions equal to 0 and solved before. What's the rule? What do I have to do first? Okay, move the first number, which would be, which 4? The last one. Isolate the absolute value first, which is going to mean subtract that 4 on the end. ISO your absolute value part first. So negative 4 equals 4 times the absolute value of x minus 3. Then what? Divide by 4. So I have negative 1 equals absolute value of x minus 3. Is this triggering any thoughts? None. Okay. So at this point, we want to split the absolute value. Oh, yeah. And we want to evaluate as if my answer was negative. So negative 1 equals x minus 3. Or this would be the positive option. And we want to flip the sign on the answer. And we want to evaluate on the other side as a negative option. So I'm evaluating negative 1 and positive 1. Do y'all remember doing this before? Splitting your branches? Okay. So I've got one option that my answer stays the way it was, and one option where my answer's flipped. And we're going to solve for x here. So I would add 3 to both sides. 2 equals x. And 4 equals x. Well, we should check it, right? We want to check for extraneous solutions, make sure we didn't do anything wrong. How do we check? Hello, Earth to you people. Plug it back in. Plug back in 2 into where?
Wouldn't it be that one, the negative 1?
I would plug it back into the top one, right here. And I would see if this statement is true when x is 2. So we got 0 equals 4 times, what's 2 minus 3?
Oh, negative 1.
Negative 1, what's absolute value? Negative 1. 1, what's 4 times 1? 4. 4 plus 4 is 0? That one doesn't work. 4 plus 4 is 8. What if we try the 4? Plug it back in right here. So 4 minus 3 would be 1. Absolute value of 1 is still 1. Absolute value is always positive. 1. 4 times 1 plus 4? 8. Still not 0. Neither one of them worked. So my answer is no solution. No solution. Neither one of my solutions worked. Now, was there a way to see that coming before we got to this point?
Can't you not have a negative?
Thank you. Amen. Look right here. This is trouble. What we're saying in this situation right here is the absolute value of x minus 3 is negative 1. No solution. No can do. No can do. I gave you a chance. I did ask if anybody was ringing a bell here. No, you can't do that. Can't have a negative number equaling the absolute value. Okay? If it had, you would continue and solve just as we did. But at that point, you can see there's no solution here. Okay? The other check on that is to think about the graph. Look at this function. What does the 4 say? Which way is it opening? Is it reflected? The front 4. Is it reflected? No, it's stretched. It's skinnier. And then the last 4 says it's stretched and moved up. This guy's above the x-axis anyway. He's not going to have an x-intercept. You understand? Okay, so probably what this looks like, it looks like it went to the right 3, up 4, and it's skinny. I mean, I'm just guessing, but I think that's a pretty solid picture. No solution. Cool beans? Now, can we find a y-intercept? In theory, no, we know it crosses the y-axis. They all cross the y-axis somewhere. How do we find a y-intercept? Plug in 0 for x and evaluate. So we're going to have 4. What's the absolute value of negative 3? 3. Good. With confidence, she said 3. Excellent. So 4 times 3, which is 12 plus 4 more, 16. So f of 0 is 16. What does that mean? It intersects the y-axis at 0, 16. So that's going to be some point way up yonder on our function. 0, 16. Cool? So you don't have to graph any of the first ones. 10, 11, 12, 14. No graphing. But you do have to have some common sense about you. It'll save you a lot of trouble if you can tell that it's not going to intersect, right? But just because it opens up doesn't mean it doesn't bump the x-axis. If it opens up and is moved down, it will. If it's opened up and it's sitting on the x-axis, it will. If it's reflected, does that mean it doesn't touch the x-axis? No. If it's reflected and moving up, it'll touch twice. Only if it's reflected and shifted down would it not touch the x-axis. Okay. And so mathematically, when that happens, it looks like I've got a negative number equal to absolute value. That's when you get no solution. If all else fails, work it all the way out and check them. Okay, that will not steer you wrong either. Do you understand if this had worked, that this would be your process? Yes, ma'am. We're good with that? Okay, fare thee well. Do your homework.